So here it is, lesson 1, quadratic functions. We are in unit 8, and we're going to start with this first lesson, introduction to quadratic functions, and I hope you guys can follow along. Now, so far we've covered linear functions, we've covered linear inequalities, we've covered systems of both of them. This is another type of function that we can graph on the coordinate plane using our graphing calculators, and it's definitely applicable to real world math, word problems that have to do with objects that are rising and falling through through the laws of like physics. It's an important concept. It's something that's covered in algebra, algebra 2, geometry, multiple sciences, and it's very relevant. It is. So we'll start off with the very definition of what a quadratic function is. Now, if you saw my introduction video, you already know that every quadratic function is in the form of y equals ax squared plus bx plus c, and a cannot equal 0, but b and c can be 0. Now, going into our exercise 1, we really first want to discuss why a cannot be 0 in our quadratic function. And I'll just rewrite the form of the function as y equals ax squared, and we'll forget bx and c for now, and we'll just focus on our leading coefficient of our first term of the function. Now, we could also write this as f of x in function notation as a of x squared. And I just want to show you that if a is 0 and we substitute 0 into our function, we now have y equals 0 times x squared. Now 0 times anything is 0. That would leave us with y equals 0. And we could do the very same thing for our function notation, where f of x equals 0 x squared, and again 0 times x squared is 0, leaving us with f of x equals 0. Now, if you recall back to linear functions, y equals 0 or f of x equals 0, if you were to plug that into your calculator, you'd be left with a straight line, an actual linear function. And again, we don't want a linear function for this unit. We're talking about quadratic functions, lines that are no longer straight. They're actually all curved. And the curvature of the line is produced by the x squared term, the first term of the function, the squared term, because it says that given an input of x, it increases at a different rate as compared to our y, or our output. All right? And that's why the line's no longer straight. So to give me a 0 as my a value and totally negate that x squared term and leave us with a linear function, this would no longer be considered a quadratic function. Therefore, a can never equal 0 rather. A can never equal 0 in this case. All right, now for letter B, we're looking at different functions. And for the most part, you can always identify quadratic functions based on them having an x squared term as the leading coefficient. Okay? Now, if we look at these 4 right here, y equals x squared minus 3 is certainly a quadratic function. Its leading coefficient is x squared, and if we graph it into the calculator, you will get a parabola. You'll get one that's right side up, a smiley face, and it will actually cross the y-axis at 3, or rather negative 3. The other one that sticks out in my mind as being a quadratic function is the last one, y equals 10 minus x squared. Now in this case, we actually have a negative x squared, meaning the a value is actually a -1, which will turn the parabola upside down and give us a frowning look, if you will. Now in this case, me being a math teacher and graphing these my whole life, I realize that this graph is actually crossing the y-axis at +10, and there's our +10 in our equation right there. But other than that, I can totally tell it's a parabola based on the fact that it has a leading coefficient and a leading term raised to the x squared power, or the second power. And then the other two are interesting. If we look at the other two, this top right one, y equals x cubed plus 2x squared minus 4, the leading term is actually raised to the third power, which would give us a cubic function, which we're not quite ready to learn about. And if we look at this other one right here, y equals x squared plus the square root of x plus 7, this square root of x actually gives us a square root function, which is more or less half of a quadratic function. All right, so both of them would not be considered quadratics. Only the two that I circled right there, or boxed. Okay. Letter C says, given the quadratic function y equals 10 minus 3x squared plus 7x, we want to write it in standard form and state the value of the leading coefficient. Now again, standard form is always written as y equals ax squared plus bx plus c. A, b, and c can be any numbers other than 0 for a. Alright, so if we just rewrite my function in my problem with the squared term first, the x term second, and then finally my constant happens to stand for c, right? Last, that is standard form of a quadratic function. And if you're looking for your leading coefficient, that's the coefficient of the leading degree term, or either leading term's degree. And if you look at that, the x squared is the highest degree of power of the function. It is our leading term, and the leading coefficient is the coefficient attached to the x squared, which happens to be -3. And then lastly, we can actually find points on these quadratic functions without our calculator, and I'll show you how to do that first. Now, anytime you're given a function and you're given a value for x, in this case we want to find f of -2 for the function f of x equals 2x squared minus 3x plus 1. You can actually just substitute in your value for x, which is -2 in this case, and find your output. So I'll do that. F of -2, and in place of every x, I'll place a -2. And I will evaluate. F of -2 equals, now according to order operations, you should do parentheses and exponents first, so I will. -2 squared gives me a +4, multiplied by 2 minus 3 times -2 plus 1. And one more step here. 2 times 4 is 8. -3 times -2 is +6 plus 1. And it looks like f of -2 happens to equal 15. Alright. So in that case, we know that a point on this graph, or a point of this function, is the point -2, 15. we could actually find multiple points of these functions, graph them on the coordinate plane without a calculator, and then connect them with a curved line, and we create a parabola. Now here's the fun part. Okay. Now, every quadratic function has a pattern. Okay, we're going to consider the simplest of all of them, x squared. All right. Now, either these functions decrease and then increase, or increase and then decrease. And they all have either a minimum or maximum point. You'll see when I fill out this table of values, it's very simple to identify where this minimum and maximum occur. Now, part A says fill out the table below without using your calculator, which is super easy. I want to evaluate this function for all of these x values. All right, -3, -2, -1, 0, 1, 2, and 3. And I want to plug it into y equals x squared for my function. Now, I'm going to start with 0. 0 squared is 0. 1 squared is 1. And again, all I'm doing is evaluating the function. I'll use f of x instead of y. And I'll take my value, and I just did 1. I plugged it in. 1 squared is 1. And I wrote it as my output. Now if I was to evaluate f of -1, take a look at this. -1 squared as an input gives me an output of +1 as well. So if I input -1, I get an output of 1. I'll do the same thing for 2. 2 squared is 4. And -2 squared is also 4. And 3 squared is 9. -3 squared is also 9. Notice there is a pattern. It looks as though we decrease, decrease, decrease all the way to 0. And then we increase, increase, increase. And if we're going this way, looks like we're decreasing to 0 and then increasing back up. Now this happens to be your minimum point of your function. Okay? Now before we do C, we'll do B, and we'll graph this function. So, if we do, we know that 0, 0 is a point. We know that 1, 1 is a point. -1, 1. 2, 4. -2, 4. 3, 9. Oops, I missed one. 3, 9. Oops, I actually missed 2. Let me go back. And -3, 9. We have my curve. Connect our points. And there's our parabola, or quadratic function. And you see my minimum. 0, 0 is right there. And if we look at this, I'm going to label this decrease in red and this increase in green. And every quadratic function will follow this rule of an increase or an increase to a decrease or a decrease to an increase, meeting at either a minimum or maximum point. They all look like the letter U, and they're either called a quadratic function or a parabolic function, better known as a parabola. Now the last thing that we're going to work on in this lesson is talking about a range. Now, I spoke about this in my introduction video. Range is where your minimum or maximum point on a quadratic function is, and all other values either above it or below it, depending on where the graph lies. Now in this case, our minimum occurs at 0, 0. And we look for our y values when we talk about our range. Now in this case, our lowest y value is 0. And if you remember interval notation, brackets and parentheses mean different things. What I just drew was a bracket. It means to include the point in our interval. If I was to draw a parenthesis, it would mean to exclude the point. Here, 0, 0 is certainly a point on our function. We will include it with our bracket. Now, all of the other points are greater than 0. We have 1, 4, 9. And actually, these points continue to go up. Hence, the arrows on the ends of my quadratic function. Now, with that being said, we actually know that these points go all the way to infinity. And infinity is not a real number. Therefore, we need to include a parenthesis to close my interval, meaning I will never get to infinity. I will not include that point, but I know that I can keep going and going and going forever. And that happens to be your range of the function in interval notation. Now we will just be working with interval notation. We won't use inequalities to represent any type of range or domain. Alright, there it is. That's page 1 of the notes. I'll post page 2 later on this week. Try to take in what I've given you today. It's a lot. It's definitely kind of a crash course, a little shock to the system with regards to quadratics. But believe me when I say it, this lesson, the next lesson, and the one after that is practicing all of what I just showed you. And it's getting into more detail of everything I just showed you. Okay? So, do your best to follow along, guys, and I'll talk to you soon.